Hello, this is Brian Albright. Welcome to the DE 24/7 podcast. I'm here today with Vincent Perrier, CEO of Nextflow Software, and we're going to be discussing next generation CFD. Welcome to the program, Vincent.
Thank you, Brian. Thank you for hosting me, and welcome to all the listeners to this podcast.
To kind of start this discussion about where CFD is going, could you talk a little bit about this idea that there's really more to it than just CFD. There's not one type of CFD that is really suitable for every engineer that is going to fit every scenario.
Yes, absolutely. Today we can see that there's a variety of different methods and approaches and tools to CFD. Of course, there are some dominant methods and tools that are industry proven. They've been used for decades, and the tools are really mature and really good at what they do. But as the problems get more and more complex, more and more specific, as the combination of physics that we want to simulate also become more and more complex, sometimes I would say the general purpose CFD solution that engineers use every day and that can address maybe very well 80% of their problems. Maybe sometimes this general purpose CFD will hit some limits, and they will need to look for alternative CFD. And in that sense, we really think that at Nextflow Software that there's no one CFD fits all, but depending on the problem at hand to be solved by the engineer, there's certainly the CFD method best suited out there, providing the right combination of characteristics that will be deliver the best results for what's being studied by the engineer.
Well, what should engineers really be looking for in this sort of next-gen CFD platform?
Sure. So, as I said, the engineers need to find and use the CFD method that is the most adapted to solve their problem at hand. And potentially, this may require using multiple methods at once, and either with some tightly coupled simulation, or in some cases co-simulation, or in other cases loosely coupled simulation. So CFD method is really the result of multiple physical assumption and numerical model choices. And today we can see on the market probably three main families of methods. You have the well-known finite volume. And you could have kind of subsets in infinite volume. You have the traditional body fitted, and you have the newest immersed boundary octree-based Cartesian finite volume. Then you have a family of so-called particle-based methods, and then the third family would be the lattice-Boltzmann LBM method. And depending on various criteria, engineers can have a look at the strengths and weaknesses of each of those methods. And some criteria, just example, could be how easy it is to do the meshing, to do the pre-processing, how long it takes to do the simulation setup with those methods. Then what are the capabilities of those methods if body motions or contacts, deformations are involved? Do they need to simulate turbulent boundary layers? Are there any multi-phase considerations or free surface that they need to pay attention to? What other complex physics are involved? Compressible flows, supersonic flows, thermal analysis, high density. There are a lot of criteria, and some methods are better for criteria than others.
When we're talking about these next-gen platforms, could you discuss the trade-offs between accuracy or fidelity and computation times, and how that's changing given some of the advancements we've seen in the compute platforms?
Sure. So when we look at next generation CFD, I believe it really needs to provide the optimal ratio between accuracy and computation time, depending on the engineer's objectives. So, as you know, CFD is more and more shifting left into the design cycle. This means once initially used at detailed design stage, now CFD is also moving up the design cycle into concept or early exploration stages. And depending where you are at this stage, maybe the need for accuracy is not that important. Maybe when you are detailed design stage, you want as much accuracy as possible. But when you are early in the concept stage, maybe you just want to have a global overview. And what really matters is to get the fastest computation as possible, and maybe just relative comparison of designs and not absolute detailed values with regards to physics calculation. So that's, in theory, some methods could be expected to be more accurate than others, but it's really use case dependent. So depending on the criteria I was explaining before, even if you try to use the most accurate method in theory that you think would work best, but maybe the use case will make this particular method not really applicable, and you will not get significant results. And after that, there are also multiple ways of implementing a method and optimizing it for accuracy or computation time. And then you also want to have a look at how the different numerical models, the different discretization choices, and other parameters that were made by the developer, the vendor of the CFD tool in support of the simulation you want to achieve. But your question was also about computation platforms. So indeed, I think we see two very important trends in computation platforms. First of all, it's GPUs are becoming more and more important. And second trend could be also virtualization. There's really a large choice of computation platforms available to users. And I believe that the CFD solutions need to adapt and to support the best platforms that the customer has chosen for this particular design stage and this particular use case. So, for example, maybe user wants to use laptops and workstation for running quick simulation as accurate as possible, but with no, I would say, imperative on accuracy at earlier design stages. And maybe they want to benefit from the GPU accelerator on their laptop or workstation. So that could be one possibility. Or maybe for detailed simulations at later design stages, they want to use HPC clusters. And in that case, depending on their strategic choice, maybe they have CPU clusters, maybe they have GPU clusters, maybe they have mixed CPU, GPU. So the goal for CFD simulation is really to make the most of the computation platform and benefit from all computation resources available to them. So the ultimate goal is always to reduce the computation time, because this is time that costs money, and this is also time that delays design choices and ultimately the time to market for the product being designed.
You mentioned that we're seeing simulation move further and further back into the design process. Can you talk a little bit about the role of automation in that type of environment where you're seeing more simulations and they're being conducted by designers who are not necessarily expert engineers in those particular types of simulation roles?
That's right. Today, simulation is here to answer questions or problems that design engineers have. And I would say for many years, design engineers have been relying on experts, simulation analysis engineers, to run simulations, to be able to have the understanding of the physics at play, and also the capability to analyze and understand the results that they observe. I think to some extent that will be always true into very detailed phases, I would say later into design stages. But more and more, when shifting left and when addressing simulation in early stages, yes, you want simulation to, I would say, in a very simplified way, to be kind of a push button, and to provide accurate and results that you can trust, but very easily for the engineer. So today, if you look at where engineers spend time in simulation, they spend time in pre-processing. So this means setting up their simulation, preparing all the files of the parameters, all the scripts, and to launch the simulation. Then obviously there's the computation time, and we talked about this before. The goal is always to reduce computation time as much as possible. And then after that, engineers retrieve the computation results and do all the post-processing and the analysis to understand, first of all, to retrieve the data, to organize the data, to present the data in a way that is possible to be analyzed by a human, to do some 3D rendering, to analyze the results, and to be able to make informed decisions on the design, and to be able to answer the initial design question they had. Really, when we look at the productivity of engineers using simulation tools, the goal for any provider of simulation solution is to reduce all this time that engineers spent and automate as many tasks as possible. So in pre-processing, this means that ideally, this pre-processing time has to be as short as possible, and ultimately like as easy as a push button. So this means engineers should be able to start from their CAD files and launch the simulation right away. So all the CAD cleaning or CAD optimization phase or any meshing phase, all of that should be automated with some advanced tools. So you do not need any expert who knows the ins and outs, the in-depths of how the solver works to adjust the CAD and the mesh to the needs of the solver. This has to be automated by advanced tools. And the same way, if you have thousands of parameters to tune before you be able to launch your simulation, that's just too complex. Simulation parameters need to be limited to a few fine-tuning parameters, and ideally, you should rely on predefined settings for identified use cases, if possible, to make the life of engineers easy. And then with regards to all the post-processing, sometimes post-processing involves also some computation for doing some rendering or for some doing just post-processing the data. All of that should be also made automatic. And I think the key for making post-processing really effective is to have dedicated tools that, again, address the application domain of the engineers. So if if design engineers are used to view some designs in a particular way, or to have a look at some particular figures, then the post-processing tools should present the data the way that design engineers are used to using them.
All right. Well, thank you very much for your time today, Vincent. I enjoyed talking to you.
Thank you, Brian, and thank you to everyone who was listening to me.